All right, Laia. So we had such a great roundtable last week. I'm excited to kind of dig into everything that came out of it. Do you want to go ahead and kick off with a recap of the presentation you ran through?
Yeah, sure. Thank you, Christine. Okay, yeah, so I would like to start by repeating the presentation on quantum neural networks applications in healthcare and pharmaceuticals before we start discussing the more useful use cases that we discovered in our roundtable. So quantum neural networks are machine learning models that combine the concepts of quantum computing and artificial neural networks. Here in the left, you see a picture of a standard classical neural network. And you can see that there are three types of layers. The first layer maps the input data into the classical neural network, which is basically a matrix of interconnected neurons that work together to produce the machine learning task. So you have this input layer, and then you have these hidden layers that try to uncover the hidden parameters of the data and extract useful features. And then these features are fed into the output layer, which output the final prediction. So all these neurons that you see in this classical neural network have hidden weights, and these weights need to be learned during the training process. So during the training process, we fine-tune the values of these weights to produce the final optimal predictions. So this is how classical neural networks work, and quantum neural networks work in a very similar way, but instead of being executed in the classical domain, they're run in the quantum domain. So we would also have three types of layers in quantum neural networks. The first one would be the data encoding, which would map the training data into the quantum system, which in this case is a quantum circuit. Then we have the variational model, which produces quantum operations on these encoded data, and it also serves as a feature extractor. And finally, we have the measurements that will produce the final predictions of the quantum neural networks. And just as classical neural networks, we have to train the variational parameters within this variational model. So from our predictions, we would construct the loss function and then minimize this loss function using some classical parameter optimization to find the best parameters of the quantum neural network. So that now that we know what quantum neural networks are, the next question is, what are the advantages of using quantum neural networks instead of classical neural networks? Well, the first advantage is the high dimensional space where the qubits live. This means that if you have n qubits, you can encode data with of size 2 to the power of n at most. So in this example, we see that we have 4 qubits. So we are able to encode data of size 2 to the 4, that is 16. But of course, as the number of qubits increases, this exponential scaling allows to work with larger and larger data sets. So this is one of the first advantages, that you can work with larger data. And the second advantage, which is also related to this, is the lower complexity of quantum neural networks. So when you think about very powerful classical neural networks, they usually need millions and millions of training parameters. So in order to properly train these neural networks, you need to learn the optimal values of all these parameters. And this means that you need very large data sets, long training times, and of course, expensive computational resources, such as expensive GPUs. But on the other hand, quantum neural networks, since they have this exponential scaling of the Hilbert space, of the space where qubits live, and they also require fewer training parameters. And therefore, you're going to need smaller data sets and shorter training times, and also you're going to need less computational resources. So this is the second advantage. And finally, there's a third one, which so quantum neural networks work in the quantum space. So the operations that are done to the data lie in this quantum space, and these can offer better performance for certain tasks. So, for example, when you're working with quantum data, and by quantum data I mean data that represents any quantum mechanical problem. such as molecules or electronic interactions within materials, these sort of problems that are by definition quantum. Applying quantum operations instead of classical operations can provide advantages in terms of accuracy of the models. So this is the third potential advantage. So now I would like to introduce a specific application of quantum neural networks that we developed in GenAI for the task of accelerating drug discovery. So the main goal was to cut expenses and duration of the early stages of drug discovery. In particular, we focused on target validation, which means that when a new biomolecule is proposed as a new drug, before going to clinical trials, we need to perform a computational study to understand the properties of this potential drug. And so if we're able to accelerate this computational study, at the end, the drugs will arrive faster to the patients. And this is the ultimate goal in drug discovery. So there are a lot of things that we could look at within target validation. And we focused on predicting the binding affinity between a potential drug and the target proteins. And this means that when you have a new drug, you want this drug to bind the protein selectively so that it can perform its function without producing side effects. So there are existing classical neural networks that are very accurate in predicting this binding affinity. But the problem is that they are very, very complex classical neural networks. This means that they have millions of training parameters, and therefore we need very large data sets, long training times, and expensive computational resources to accurately train these models. So in this project, we designed a hybrid quantum classical three-dimensional convolutional neural network to tackle this problem. So in particular, we took a 3D CNN and we replaced the first layers of the CNN by quantum layers. And by doing so, we reduced 20% the number of training parameters. So we went from 10 million training parameters to 8 million training parameters. And this in turn meant that we had 20 to 40% savings in training times and costs derived from using expensive GPUs. And finally, the third advantage of using this approach is that it can be generalized to other use cases that involve using quantum neural networks or convolutional neural networks. So this is not just particular for drug discovery, but we can generalize this approach to other problems. And this is why we're here today, because we want to discuss what possible applications of these kind of neural networks, quantum neural networks, we can find. So we have wrapped this up into a library where you can run different types of quantum neural networks to solve specific problems. So before starting the discussion of the most useful use cases that we discovered in the roundtable, I wanted to outline some of the applications that we already know. So the first one would be using quantum neural networks or quantum convolutional neural networks for medical images. And this means performing object detection or image matching for early detection of diseases. And this could be applied to oncology by performing early detection of cancer. Then we have quantum reservoir computing or physics-informed neural network to simulate quantum mechanical processes such as molecular data. And in this case, what we're doing is we're mapping the input data into a quantum space, into a quantum system, and then we're letting this system evolve naturally. And we're then gathering information from this system to understand their dynamics and understand the physical system. So this is very useful for quantum simulation, such as simulating the properties of molecular data or the electronic properties of new materials or chemical reactions. Then we have tensor networks. And tensor networks are quantum-inspired algorithms and that have the potential to be applied to a large space of applications. Some of the applications that we think are interesting are neural network compression. So we've been talking about how classical neural networks have a lot of training parameters and and this is a bottleneck for the training of these neural networks. So tensor networks can be used to compress these classical neural networks so that they have less training parameters, and therefore they can be trained with less data and shorter training times. Then also tensor networks can be used to design new architectures of neural networks using quantum-inspired architectures to produce better results. And finally, another application of tensor networks is filling missing data. So if you have a large matrix, a tensor, where you have a lot of missing points, tensor networks can be used to approximate this tensor and thus fill all these missing points. And finally, we also discussed anomaly detection for clinical data. And this means detecting outliers within clinical data sets using quantum neural networks. So these are the high level use cases that we started the discussion with. And now we would like to introduce the use cases that we discovered in our roundtable.
Yeah, and actually just starting with the outlier detection, one of the kind of high level use cases that came up was adverse drug event monitoring and reporting, and how this could be applied to there. Do you want to talk a little bit about, I guess, the outlier detection aspect of that?
Yeah, so adverse drug events means predicting where a drug is going to cause a very significant side effect, for instance, that is going to be dangerous for the patients. So one way to tackle that would be to study the patient characteristics and look for any outliers to identify if this patient is different in any significant way that could mean that they could have an adverse reaction to a certain drug. And for that, we could use outlier detection to analyze the properties of each patient and thus produce personalized medicine to them.
Okay, so that was an interesting one that came out. There's a lot that we would have to, I guess, dig into to further validate that. Like, we need to make sure we've got access to the data, right? That the data recorded has,
Yes,
data
and
quality is
it's not
accurate.
clear what kind of data is relevant. So, and these
Right.
might vary from drug to drug. But yes, it's a very significant problem.
Lot of variations there, but yeah, so
Yeah.
that one was an interesting one. And then another one that came up that wasn't actually in the healthcare space, but was interesting was satellite images. Do you want to talk a little bit about that one?
Yeah, so it was said that so we've designed these convolutional neural networks, and the idea is that these neural networks provide very significant advantages, especially when the images have a lot of channels. And by channels, I mean, for instance, in normal images, you would have 3 channels, the RGB channels, the color normal ones. But if you have different type of images, you can have multiple channels giving different information about these images. And quantum neural networks are able to look at all these channels at the same time, and therefore they can provide significant acceleration in the training and well, yeah, and accuracy of these models. And it was proposed that this could be very useful for satellite images, because they have images with lots of channels encoding different information. This is also a very vast problem, and I'm sure there are a lot of applications within this space. But yeah, I think it's also very, very relevant because it's one of the problems where quantum neural network can really provide clear advantage in the shortest term. So yes, I think it's very, very significant.
Yeah, and just a note for anyone watching, the more that we've got, people that can bring forward these, use cases, these data sets, and kind of work with us to really build them out and understand them deeper, it really helps us then further unlock even more use cases within this. So that's really kind of the biggest stage we're at right now is we understand, I think, these high level umbrella use cases. It's now getting the right partners, the right customers, the right, people around us in the industry side that can really help us now start seeing these problems all the way through end to end. And I guess the last one, major one that came up was healthcare supply chain dynamics. And what was interesting about that is that there's actually two ways of tackling this, right? There's the overall optimization of the end-to-end kind of process, but then there's also, I guess, the smaller predictive modeling pieces that we can kind of pluck out of that we can potentially bring some nearer term advantage. So do you want to talk a little bit more about that one and how we see that one evolving?
Yeah, so yeah, supply chain optimization is a very relevant use case, I think, across all industries, but especially in healthcare, it's also very relevant. And yes, as you said, it's a very complex problem. There are a lot of factors to take into account, and looking for end-to-end solution, taking everything into account, I think it's possible, but it's definitely longer term. But one thing that we could do shorter term is look at the specific blocks of this optimization and try to accelerate them using quantum computing. So an example would be predicting the amount of materials that we're going to need to produce a drug, or some sort of forecasting of cost or delivery times. These sort of little pieces that add up to the whole problem. These could be optimized using quantum computing, in particular quantum neural networks, and then the whole project, the whole process, the whole supply chain network. Optimizing the whole thing, of course, would be a longer term application of quantum computing.
And for those that don't have as much of a understanding or background between kind of the compute power required for an optimization problem of that size compared to the compute power required for, the neural network packages and even some of the hybrid solutions that we're looking at, can you talk through a little bit about that?
Yes, it's true that, of course, this is going to depend on the amount of data, the size of the data, the complexity of the problem itself. But yeah, when you're using quantum neural networks, at the end, you're solving specific problems. So you're only going to use data to solve a very particular task. On the other hand, when you're trying to solve the whole network problem, you're going to have to take all the data into account. And of course, the scaling of this problem is much more complicated. And we would need probably thousands of error-corrected qubits. And this is a bit far away, but still within 10 years, I would say. So not that far.
Far, but
Yeah.
not that far.
Yeah.
So going a little bit deeper into the use cases, oncology has been an interesting space that we're exploring more deeply, right? Like there's a lot on the imaging diagnostic side that I think we can add value. And I had a really interesting conversation on Friday with a guy who's using deep learning for lung cancer diagnostics, and lung cancer diagnostic imaging more specifically. And it was really interesting because I think that's a perfect, when we think about taking it out of these high level umbrella use cases and bringing it into an actual, tangible use case and tangible problem, I think that's a great one where we can really see this kind of all the way through, take our existing package, apply it to that data set, that problem, and really see where we can optimize. And those are the use cases I think we want to keep plucking out more and more of those, right? Where we can try different data sets, apply it to different types of problems. And so that was one that we were able to go a little bit deeper and I think is promising. And then another one was the skin cancer detection. So would you mind just talking through your thoughts on both of those?
Yeah, I think they're definitely very, very relevant, and we could definitely use our library to tackle them. And they lie in the category of using quantum convolutional neural networks for medical images. So yes, I think this goes into in the direction of using personalized medicine and trying to build more accurate model for early detection of cancer. So I think these are more specific use cases than the other ones that we found at this roundtable, and they are definitely worth exploring. And I think our quantum neural network and image processing package, because it's also an image processing using quantum computing package, could be very useful for dealing with medical images. And of course, lung cancer is it's very relevant, and also skin cancer. And I think we mentioned that regarding skin cancer, there was a bias regarding the darkness of people's skin. So if you have a lighter skin, it was easier to get more accurate detections. But if your skin is darker, it was harder to detect skin cancer. So we could also look at that and see how we could use quantum neural networks to try to reduce this bias, and find more accurate predictions for everyone.
Yeah, that would be amazing. I love seeing it come all the way down into solving actual problems. And there's so many, like, I make jokes about our library being literally the problem solver of the world, right? It's like, let's just pluck out all these different use cases, because it's like you create one model, we create one package, and it just unlocks so much. And what's really great about a lot of this stuff is, these are near term, right? These are things that with the hybrid and the scalable into the fully quantum, and even the fully quantum is not using massive number of qubits, right? So it's just, we're in that kind of early stage and early application with some of these, and I just think it's exciting to be able to start realizing some of that advantage now, right? It's not something that, as many people may think, that's 5, 10 years, 20 years down the line as the hardware matures. We're really starting to uncover use cases that we can add value to today, and it really lights me up. It gets me so excited. So the loaded question, Laya, is now have you learned, and I know we're gonna have several of these series of the use cases, right? And continuing to dig deeper and deeper with the industry folks out there. But in your mind, what are the next steps for kind of validating and prioritizing the work in our library with the existing package, and then any kind of future models you might want to explore or bring into it?
Well, I think first we would have to look for more specific use cases within these big umbrellas that we're discovering now, and then also discover if there are data sets that are available for this task, if we would have to partner with someone else to get the data, and also understand more the industry, because the more that we understand the real problems, the bottlenecks that they're being faced right now, the more that we can provide value. So yes, I would say that we need to really go deeper into specific use cases, look ways that we can provide value using quantum neural networks, and then build end-to-end applications of these problems. And any knowledge that we get from them, we can add to the library, and it will be a more powerful tool for future users.
Yeah, no, I agree. So we've got our work cut out for us.
Yeah.
We got our summer projects ready to go. No, this has been good. I guess, is there anything else from your side that you want to share with the group?
No, I think that's all. I just feel free to reach us with ideas or questions or anything that you want to discuss, and we're looking forward to future conversations.
Yeah, keep your eye out for our future events in our series. So
Yeah.
thanks everyone for watching.
Thank you.